Hi everyone, my name is Vanneste and I'm a PhD student in the research group IDLab from the University of Antwerp and IMEC. I will be presenting the work we did on the paper Learning to Communicate using Counterfactual Reasoning. We will focus on the cooperative multi-agent reinforcement learning setting. In this setting, multiple agents are trained using reinforcement learning, and we will use the shared team rewards in order to promote cooperative behavior and learn how to achieve a common goal. Additionally, we will use the centralized training and decentralized execution paradigm. This means that during training, the agents have access to the policy of the other agents, to the observation of the other agents, and can have access to a centralized critic. However, during execution, the agents only have access to their local policy and their local observation and do not have access to this centralized critic. In our work, we specifically focus on communication between the different agents. This communication can be used to share relevant state information or even share strategic information on how to achieve our common goal. However, this communication is not predefined, but we will learn this communication simultaneously while we also learn on how to behave in the environment. We will focus on the one time step delayed discrete communication setting. This means that it takes one time step for a discrete message to go from one agent to the other one. This figure shows the Markov decision process with communication. In this figure, we see two environments. The bottom environment is the action environment, which is traditionally used for reinforcement learning. We can see that the agent receives an observation from this environment and can perform an action towards this environment. Based on the choice of action, the agent will receive a certain reward. On the other hand, the communication environment, every agent will receive a batch of messages from the other agents and will be able to send a message itself towards the communication environment. The communication environment itself will define which messages will go towards which other agents. We can also see that the agent has two policies, a policy for the action environment and a policy for the communication environment. These policies are independently trained. Our work extends the work on counterfactual multi-agent policy gradients. In this paper, they present the COMMA method, which focuses on the create assignment problem within multi-agent reinforcement learning. They will do this by calculating an actor-specific advantage using a centralized critic. The advantage is the difference between the Q value of the joint action U and the expected Q value when following the action policy. This advantage will show if an action was better than expected and should be encouraged or not. The decentralized actors will use this advantage to calculate a policy using the policy gradient method. However, there is no distinction between an action and messages within COMMA. This means that the non-stationarity in the communication environment, due to the changing policy of the other agents, can prevent a critic from converging. In our paper, we presented the multi-agent counterfactual communication learning method, also called MAC. It will use a centralized critic and use counterfactual reasoning to calculate a policy-specific advantage, very similar to the structure of COMMA. However, we will learn action and communication policy separately using a separate advantage calculation. The figure on the right shows the high-level structure of MAC. It has the communication environment and the action environment, the two different actors, and a centralized critic. The actors will send during learning all the available information towards the critic, and the critic will use this information in combination with the full state and the team reward, in combination with the M function, which defines which messages get sent to which agents, to calculate an action advantage and a communication advantage. This slide shows the action advantage calculations and the communication advantage calculations. They have been adapted from COMMA to include incoming messages, but apart from that, they look very similar. However, when we look a little bit closer at the communication advantage, we see that we need a communication queue function in order to calculate a communication advantage. But how can we learn a communication queue function in a non-stationary communication environment, which is non-stationary because the policy of the other agents will change the utility of a certain message? We will not learn the communication utility, but we will use the policy of the other agents and the action utility to calculate it. The communication utility can be split up in two separate utilities. First, the communication policy to action policy utility is defined as the expected utility in the next state when selecting actions following the action policy when receiving a certain message. Similarly, the communication policy to communication policy utility is defined as the expected communication utility in the next state when following a communication policy which received a certain message. The communication utility to action policy utility can be calculated using an exact method. In this exact method, we sum over all possible action permutations and calculate the utility for an action permutation, which is multiplied by a chance of selecting this action permutation by the different policies. The computation time for this will scale exponentially, which is of course undesirable, which is why we looked at two alternative approximation methods. First, we look at sampling mean, in which we sample the action permutations from the different action policies, and we will look at the utility this will represent. These utilities will be averaged out, which will lead to an approximation for the real QCU value. Alternatively, we looked at the agent-based sampling, in which we will iteratively go over all the agents using the exact method, and the action permutations of the other agents are created using the sampling mean method. In our paper, we prove that this is a valid approximation for the real QCU value. The communication policy utility can be calculated using the exact method. However, this will be too computationally intensive to calculate, which is why we use a combination of agent-based sampling and a specifically designed algorithm. This algorithm will first start with calculating QCU at every time step. Then it will move on to the terminal time step t. At this time step, QC and QCU will both be 0. Then it will move on to t minus 1, at which QCU will have a certain value, and QCC can be calculated using QC from the terminal time step. Both QCC and QCU can then be used to calculate QC at t minus 1. Next, we will repeat the process for t minus 2, t minus 3, and we will continue until t is equal to 0. During our experiments, we discovered that the policies were sometimes completely ignoring the received messages. When we, for example, look at the action policy, when the action distribution is always the same independently of the incoming messages, we can see that the communication advantage will always be 0. And when the communication advantage is always 0, the communication policy cannot learn anything. And when the communication policy cannot learn anything, the action policy will not use the received messages. This will of course prevent communication from being learned, and that's why we introduced the social loss function. This social loss function will encourage the policies to use the received messages. We will do this by taking the absolute difference between the policy distributions between receiving a certain message and receiving a certain message when a single bit is flipped. It's also possible to use alternatives to the absolute difference like KL divergence, but we found in our experiments that the absolute difference was the best option. In our experiments, we compare MAC against COMA and MLDPG. We compare against COMA because MAC is of course an adapted version of COMA, and it's interesting to see how these changes influences the results. We also compare against MLDPG because it's a baseline that's quite often used in the state of the art. We have 4 different versions of MAC. So we have MAC exact, which doesn't use any approximations. Then we have MAC sampling mean. We have MAC agent-based sampling. And finally, we have MAC exact without social loss function. This is of course used to see how the social loss function influences the results. We've evaluated these different algorithms on 4 scenarios of the particle environment. We also have a scalability test on the matrix environment, but for this environment we reference to the paper. The first scenario of the particle environment is the speaker-listener. In this scenario, the listener has to navigate towards the proper target landmark. However, the listener doesn't know which of the landmarks is the target landmark. This information is only available to the speaker. So the goal of this environment is that the speaker encodes this information into a message. This message will be sent towards the listener, and the listener will use this message to go towards the proper target landmark. If we look at the results, we can see that the MAC methods are able to learn a valid communication protocol. However, we also see that the MAC sampling mean gets stuck into a local optima. We can also see that the MADDPG and COMA methods are not able to achieve the same level of performance as the MAC methods. This is caused by the critic not being able to properly evaluate the messages due to the non-stationarity of the communication environment. The second scenario of the particle environment is a simple reference. This scenario is an adapted version of the speaker-listener, in which both agents are both speaker and listener. This means that the agent have to navigate towards a target landmark and have to communicate the target landmark of the other agent to the other agent. When we look at the results, we can see that MAC exact can slightly outperform the approximation methods, and MAC exact without social loss is outperformed by all other MAC methods. This clearly shows the importance of the social loss function when learning to communicate. MADDPG and COMA are not able to learn a valid communication protocol. The next scenario of the particle environment is a speaker with 3 listeners. In this scenario, there are 3 listeners that have to navigate towards their own target landmark. This information is only available to the speaker, so the speaker has to communicate their target landmark to all the different listeners. In this environment, we can see that MAC agent-based sampling is able to perform very similar to MAC exact method, while MAC sampling mean and MAC exact without social loss have much more trouble of reaching the same level of performance. We can also see that MADDPG and COMA are not able to learn a valid communication protocol in this specific scenario. The final scenario of the particle environment is a speaker-listener with broker. This is an adapted version of the speaker-listener in which the speaker and listener cannot directly communicate, but have to go through the broker agent. So the goal of the environment is for the speaker to encode the target landmark of the listener into a message and send this message to the broker. The broker will re-encode this message and send a new message to the listener. The goal of the listener is then to go towards the target landmark. When we look at our results, we can see that MAC agent-based sampling is able to perform very similar to MAC exact again. And we can also see that only methods with the social loss function can learn a communication protocol, which again shows the importance of the social loss function. To conclude, we have introduced counterfactual reasoning in the communication environment, and we have shown that MAC is able to outperform the baselines in the different scenarios of the particle environment. We have evaluated 2 different approximation methods, and we have shown that agent-based sampling is able to achieve very good results while scaling linearly with the number of receiving agents. Finally, we have introduced and evaluated the social loss function. This social loss function was created to promote communication learning, and we have shown that MAC with social loss function is able to achieve better results than without the social loss function. Then I would like to thank you for your attention.